Okay, so I think everybody in the room knows who I am, but for the purposes of the recording, I'm Richard Bunt. I'm a software developer on the Forge team. I've been on the team maybe 6-7 years. I've lost count, to be honest. At the moment, I'm the technical lead for our HPC patches on top of GDB. Now, this talk was inspired by a talk that I saw at Connect last year about the successes of upstreaming and the benefits that that can bring relative to keeping your patches in a downstream, out-of-tree mess. And I wanted to tell a similar story for Forge. So I'm going to start by going over a bit of HPC background, and then I'm going to cover some of the modifications that we've historically made to our GDB. Talk about the downstream pain and then the relative upstream bliss that came with our efforts there. So what is high performance computing? Well, it's basically regular computing, but it happens on lots of machines simultaneously, usually with some communication between all of these machines performing this computation. So some examples. I've actually nicked this slide from my colleague Dirk, so shout out to him. So you can use this to simulate galaxies and weather forecasting. Why would we do this? Well, we can't really simulate a galaxy any other way because that would require a ridiculous amount of resources. Other examples, computational fluid dynamics and crash simulations. Why would we simulate these? Well, because it's very expensive to keep throwing things in engines, because engines are expensive. So it's preferable to simulate that to save money. We typically find that HPC simulations are written in Fortran, C, C++, and some Python to glue it all together. And to orchestrate the different machines, we use an implementation of the message passing interface. This allows you to send point-to-point communications between the different nodes in your simulation, or collective operations such as broadcasting a single piece of data to multiple other machines. So how do we debug such applications? Well, this is Lenaro DDT. It's a bit like any other front end that you would expect to a debugger. It's got play, pause, step in, step out in the top left. But what makes this different is that we try to aggressively aggregate data to make it easier to see what's going on with your large-scale runs that may be over tens or hundreds of thousands of processes. This example is just over 16, just to make it easier to explain. And what we do here is we aggregate the stacks, this example in the bottom, where we've got 15 processes on one line, and one of them has advanced further in the application. And the other example is for variables. We annotate them with spark lines, so you can get a feel for how the variable changes over all of your processes. This is also Dirk's slide, and my addition is that I've sent a command to the underlying debugger, and we can see that this is actually just GDB under the hood. However, we've had to modify GDB to make it more amenable to debugging HPC applications. We've had to add additional Fortran support. The upstream support for this language wasn't particularly strong. Also in HPC, you find that you don't just use the GNU compiler collection, you tend to have a lot of third-party compilers in the mix as well, all of which have their own interpretations of the DWARF standard. So we've had to make some improvements in this area. Stability is also something that we care about. If you're just doing single process debugging, you might not notice a race condition, but as soon as you scale that up to the node level and the machine is under more load, these race conditions can appear. Equally, if you're launching hundreds of thousands of GDBs, that increases the probability that you're going to see a race condition appear as well. And we've had to fix things in this area in the past. And I'm going to skip over GPU GDBs for today. So next, some examples of how we've had to change GDB. So HPC applications typically contain very large multi-gigabyte arrays. They represent the simulation space, so your galaxy or the atmosphere in the case of weather forecasting. Sorry, I realize I've forgotten to go over one of the points on this slide. Memory efficiency is also very important. Typically, when you build a supercomputer, you don't, say, have double the amount of memory in the machine, because that would just increase the cost of the machine. So you're looking at maybe some small percentage of headroom. What this means is that you don't have a lot of room to run tooling on these machines when the application is running. And in some cases, people actually build performance models to project exactly how much memory that application is going to be using at a particular scale, and then they provision the machine with that much memory. So yes, memory efficiency is important. So if you use GDB to print one of these large arrays and you say request 10 elements, it will dutifully print those 10 elements out. But GDB will by default try to take a copy of the entire array, even though you only want 10 elements on the screen, which is not great because you can't really afford to double your memory usage. GDB does have a feature to handle this. You can set the maximum number of bytes that GDB will load in. Unfortunately, if you do this, it will just refuse to print the array at all, rather than trying to make use of the memory that you have given it to work with. So we modify GDB so that it will do what it can with the memory that it has at its disposal. So if you give it a 100 bytes limit, it will print out as many elements as it can with the bytes that you've given it. This work is not currently upstream, and the full answer to why that is could be a talk in itself, but we have started to migrate some of this functionality upstream. But the main point of this slide was to show how we have and why we have needed to modify GDB. So next example, Fortran array slicing. So like Python, Fortran does support array slicing. So if you have, in this top example, you have an array of 10 elements, you can just print out from 2 to 4. Note that Fortran is indexed at base 1 rather than 0. And the story here is that there were typically 3 implementations of this hanging around. One in upstream, one in downstream Forge GDB, which is basically the upstream implementation but with fixes that customers had reported. And there was an implementation hanging around in Fedora as well. So the upstream implementation was flawed in that it didn't support all forms of array slicing, but it was very memory efficient. When I first saw the Fedora implementation, I was quite excited. So I thought, oh, this supports all array slicing. But when I ran it through our test suite, we started running out of memory, which made me look into how it was implemented. And unfortunately, it is memory inefficient. What it does is if you want a 1D slice of a 4D array, it will first take a copy of the 3D slice, the 2D slice, and then finally the 1D slice. So you have this hierarchy of memory usage. So we actually set out to create an implementation that satisfied all the requirements, so all slicing, and it was memory efficient. And this is now upstream. So you can take a copy of stock GDB and you can use all of this today. And hopefully Fedora can remove their downstream patches. So another example. Typically, you keep your source code on a HPC system on a shared file system. And what you don't want is tens of thousands of GDBs trying to open the same source file at the same time. Anecdotally, this is a bad idea. This has been passed down to me by my forebearers. So we have added options in GDB to control which files are opened. This also affects the init files as well. So yeah, you can play with this option in upstream GDB now. And if you're wondering how Forge handles this, because we still need access to the source files, but we have our own scalable mechanism for handling this information outside of GDB. We still use GDB to get the file names, but we use a different mechanism to actually get the source code. And my final example, so this is about controlling how much data we print out when interrogating variables. So in this example, I have a struct of arrays, and you can use this max depth option to incrementally print out more and more of your data structure. So if you print out coordinate psi with a max depth of 0, you basically get nothing. But if you increase that to 1, you just get the names of the arrays printed out. Now this is important because you can effectively use a tree view to incrementally go deeper and deeper into your data structure without printing out, say, 3 whole arrays at the same time. And we combine this with our length-limited printing to allow us to control exactly how much information gets printed. And that's shown in this last example here, where we set both the max depth and the number of elements we want. And Forge typically runs with a combination of 0 and 1, so that we can only extract data that the user actually wants to see without ooming the machine. And this patch is actually fully upstream as well, so you can go away and play with this in Upstream GDB as well if you want to. So that's just 4 examples. At the height of our depravity, we had over 400 of these additions. And it was getting to the point where we were moving these patches from older versions of GDB to newer versions of GDB, and we're saying we don't want to do this again. This is just not working for us at all. And it was also reaching the point where we had to abandon rebases because it was taking so long that the next version of GDB had come out before we'd finished rebasing our patches on a particular version. This is what happened with 7.10. We just did not finish. And based on this chart, we can see that actually this problem wasn't going to get any better without some external force. So just to cover this chart in a bit more detail, on the x-axis we have GDB version, and on the y-axis we have number of patches. The reason I've chosen to use number of patches rather than say lock is I find that patches is more useful for thought experiments around the intractability of this technical debt. Because if you've got 400 things to know about and you say, okay, I want to add a test case for each of these 400 things or know about each of these 400 things, that's going to take you over a year if you want to spend a day on that. That's just not really possible. And I'll admit, I do not know exactly what all 400 of these patches ever did, because I can't really afford to spend 2 years of my time just learning about the patch set. So we thought, well, okay, there's got to be a better way of doing this, and this is quite clearly polishing these patches and contributing them to the upstream community. And this is what we started doing around GDB 8.2. And we were managing to upstream, I can't remember the exact numbers, but maybe 10 or so per year. And if you run the numbers against 400, well, this is going to take a very long time to upstream the entire patch set. So we also needed kind of a secondary method to pay down this debt. And what you see in that top bar is a representation of where our patches went relative to our high point. So in orange, the patches we actually upstream, so it's about 30 or 40 in total. But what this allowed us to do around the GDB 9.1 era is that for the first time, we could actually run a stock GDB within Forge. And this was important because it meant we could run our test suite on a stock GDB and actually see where the gaps were. So what we decided to do is do this and rebuild our patch set with just the patches that we had test cases for. And doing this, we were able to eliminate all the patches in light blue, which is actually about half the deck. And in parallel with that, we were able to identify patches that were quite clearly just not needed anymore for compilers that had been dead for quite some time. So we were able to cut those off. So while upstreaming didn't contribute to the directly to the largest pay down, it did allow us to pull us out of this mess much further and much quicker than we were expecting. So this graph is a representation of where we are today. We're in a much better place with GDB 13. We've been able to reduce our patch set down to about 50 or so from 400, using Upstream as a starting point. And we've also done some pay down by converting some of the code to Python plugins as well. So we have a few other methods other than upstreaming for getting rid of our patches when it doesn't make sense to upstream them. So just to summarize the wins that we've derived from this, well, everybody can benefit from the work that we've done here, especially in the case of array slicing, where we've hopefully been able to reduce the maintenance costs for not just ourselves, but other people as well. The one example that I haven't been through in the slides that stood out is the support for isolating Python in GDB. This stood out because somebody actually came onto the mailing list and said, actually, this benefits us as well, because we're doing a similar thing to you. We are using and shipping Python with GDB as well. So hopefully they were able to eliminate some of their local debt as well because of the work we put into that. And And for us, selfishly, we've been able to reduce our time to rebase. Now it says months on here, but in terms of lead time, back in the 8.2 days, it was taking us a good 12 months from saying we need a new GDB to it being in production in the product. That's 2 release cycles for Forge. But now that we are around 50 patches, we can be more reactive and we can say we need a new GDB, and then within 4 weeks or so we can have a new debugger that's ready to go out in our next release and being used as the main debugger that we recommend our customers use. I'm going to skip over the next point because that's GPU GDBs, and I don't have time to go into that today. And then the final example is that because we are closer to upstream, we can now actually make the suggestion that customers use the GDB which is on the system itself. And we use this in a recent support case to enable a customer running on Graviton 3, because the system GDB had patches that we didn't currently yet have in the GDB we were using with Forge, and that worked to unstick them while we were able to bring those patches back into, those upstream patches back into our tree. So the future, projecting that we'll have fewer patches on GDB 15. We're not currently planning to do a GDB 14, but I won't go into why that is, because that's related to GPU GDBs. And we've got more plans to create more plugins in Python as well, and hopefully continue upstreaming as time permits. So yes, upstreaming has paid off for us very much. Thank you very much. Are there any questions at all? No questions? Okay. Thank you very much for listening. It has been a pleasure.